Okay, so this is problem number 5 of Bernoulli. So if you go back to worksheet number 13, we still haven't finished the Bernoulli problem. So all of you guys have finished the hydrostatics, as far as I've double seen. And so remember there was the 2 hydrostatics problems, and then there was like the 9 Bernoulli, or how many ever there were. So what I'm going to do right now is all the Bernoullis. Finish them off. So you guys got through number 4. Remember checking those off. Review those. But now I'm going to go through 5, 6, 7, 8, 9. So 5 is kind of an interesting one. It is from a past test. And so the way you're going to want to start, I actually have to look at the camera for this one, is you want to start with the free body diagram. So that's what you see there, okay? And so for the free body diagram, it's the gravity balanced by the pressure. So see the pressure right there, balanced by the gravity, the weight. And so what you do is it's a statics problem. So this doesn't have a buoyancy because it's not that the plate is sitting inside the water. And remember, for buoyancy, it's the displaced volume times by the density of water times by gravity. And because this plate is just sitting on the top of the water, there is no displaced volume. Okay, so there is no buoyancy force. But we do have the weight of the plate is balanced by the pressure of the water underneath. Okay, so that's what you're seeing there. And so the sum of forces should be 0 for it to be a static problem. And so what we're asked to find is the mass of the plate. And so when you do this, you get the mass in terms of P1 times by pi d squared times 4g, which is what you see down here at the bottom, right there. But you don't know P1. P1's an unknown. And so then you need to use Bernoulli, okay? And remember, one of the things I told you guys is know when to use Bernoulli versus when to use a hydrostatic equation. And so when there's water moving, then you're going to want to go to Bernoulli. Okay? Now in this one, it turns out it's interesting because we're going to use Bernoulli to find P1. The reason it's interesting is it turns out that the answer is hydrostatic. And there's a reason for it, a physical explanation. So remember, when you're doing a Bernoulli, the things I would expect from you guys, I would expect a datum point. So don't be lazy like your QSI, write datum, or D, I guess I'd be lazy, but still. And put the 2 points you're evaluating at. You have to put that down. If you don't put it down, then when the QSI is looking at, what you're writing down as your Bernoulli equation, and they don't know what points 1 and 2 are, if you have a mistake, it's hard for us to say, oh, okay, I see what they're doing. We're not mind readers, right? You guys aren't, we aren't. So if you guys put down which points you're evaluating at, it's a lot easier for us to see if you guys understood it or if you guys made a silly mistake. Whereas if you guys made a silly mistake and you didn't write it down, then we're just going to assume you guys don't know. Okay? So don't let us do that. Okay, so we go to our famous Bernoulli equation. Let me see if I can see all that. Okay, so Bernoulli's is right there. And so when we do that, again, this represents conservation of momentum, right? And so this is equal to a constant, and this is equal to a constant, and when you're following a streamline, they have to be the same constant. So what we're going to do is we're going to take a little particle underneath the plate, okay? And then we're going to go to the point right where the fluid is going to stop. Okay, so when we do that, let's first look at what happens at point number 2. Number 2 is a little easier. So I'm going to set my datum at 1. So that does make the GZ1 term go to 0. But when I set my point here, now remember, Bernoulli worked with either pressure being absolute or gauge. It's a lot easier to work with it being gauge pressure. But be aware of what you're doing. So if you guys recall, the definition for P gauge was equal to P absolute, let's do it that way, is equal to P gauge plus P ATM. So if this is open to the P ATM, then the absolute pressure has to be P ATM, which means the P gauge has to be 0. And that's why any time this was set open to the atmosphere, P gauge was equal to 0. So P2 goes to 0. Okay, because we're going to work in gauge pressure, and because 2 is open to the atmosphere, it's 0. Now, we also chose a very specific point when the fluid is about to start falling back down. So that's going to let V2 go to 0. So those are 2 of our assumptions. If you guys really want to be fancy, show off to the QSIs during the test, write down your assumptions. Okay. And even write down, because open to the atmosphere, because, it's about to start falling down. Now, V1 is that tricky little guy where it's because his plate is so big. So this is kind of an odd problem. I wouldn't have thought to do it for a while before, it took me a while to get this one. So the particle's going to do something like that. He starts off underneath the plate and goes to the opening and then goes out. So this opening I've denoted as 3, okay? And that opening's really tiny. And I believe it's written in the problem. And the reason that's written in the problem is that if you let that opening be 3, okay, then that A3 is really tiny compared to that A1. And so A3 over A1 is a small number over a very big number, relatively speaking, so it's a very small number times by its velocity. So that means V1 can approximately be 0. Which makes sense. V1 can be thought of as 2 ways. Because the water is going up out of here, then it can be thought of as the water line coming down, okay? It can also be thought of as some fluid particles trying to cascade over. And that is going to be small compared to the water fluid shooting out. So for physical reasons, it makes sense that V1 is approximately equal to 0. And it all hangs on the balance that the opening is much smaller than the container. Okay? So for that reason, V1 goes to 0. And we already stated that we put our datum here, so that's 0. So what ends up happening is that because the way we've evaluated V1 being 0 and V2 being 0, then this has turned into rather a hydrostatic problem because we've allowed it so that both the velocities are 0. And so it's rather turned into, we're looking at the column of water, and then we're going to look at the pressure exerted at this point of the column of water. So, be careful though, because the QSI will want to see Bernoulli if they see a moving fluid equation, okay? So anytime the water is moving, go to Bernoulli. If the water is standing there, like those walls we were doing in class, then that's hydrostatic, okay? So what we end up getting is on this side we only get P1 over rho, and over here we get GH. So we do get a hydrostatic, and then we turn that in and we find M. And again, that makes sense because in this one we've chosen the 2 points where the velocities happen to be 0. So what we're really evaluating is the pressure due to this column of water onto a particle right below it. Okay? So that's number 5. How do you stop recording?